Welcome back to QHSE Talks. Let me start with a reality check that every safety professional eventually has to face. Personal protective equipment is not about comfort. It's not about convenience, and it's definitely not about looking compliant. PPE exists for one reason only, because a hazard still exists. Every hard hat, every glove, every face shield, every respirator tells a story, and that story is never, "We designed the hazard out." The story is, the hazard is still here, and now the human body is exposed to it. That's why this chapter matters so much more than people think, because PPE is where safety systems stop being theoretical and start becoming personal. This is the point where risk management ends up directly on someone's head, in their lungs, over their eyes, and against their skin. And here's the uncomfortable truth. PPE is unforgiving. Engineering controls can fail gradually, administrative controls can be misunderstood, but PPE fails immediately, and often violently, when it's selected wrong, worn wrong, or trusted too much. A glove doesn't warn you it's incompatible with a solvent. A respirator doesn't tell you the cartridge is wrong. Eye protection doesn't announce that the shade number is inadequate. The human body finds out first. And for CSP candidates, this chapter is dangerous if you treat it like a list of equipment types, because the exam and real life doesn't care whether you can name PPE. It cares whether you understand when PPE is required, why it's required, and what its limits are. This is also where liability lives. Written hazard assessments, employer payment responsibilities, training requirements, fit testing, maintenance, and enforcement. Miss one step, and PPE becomes a false sense of security instead of protection. So before we talk about volt ratings on hard hats, before we talk about NRR calculations, before we talk about glove materials, lens shades, or respirator types, we have to step back and ask a more fundamental question. Why is PPE needed in the first place? Because PPE is not a strategy you start with. It's a strategy you arrive at after everything else has failed to fully control the hazard. And that foundation is where this chapter really begins.
It is. But before we get into the numbers on the gloves and the shades on the lenses, we have to start at the beginning. We have to lay down the foundational principle that governs all of it.
And that would be the hazard assessment. It's always the first step. It has to be.
It is. And it's because PPE, as a strategy, it's the last resort.
Right. The last line of defense.
Absolutely. We have to keep hammering this point home. PPE is the final barrier. The second an employee has to put on a respirator or a pair of safety glasses, it's basically an admission.
An admission that the other controls, the upstream ones.
Right. Elimination, substitution, engineering controls, that they've either failed to completely get rid of the risk, or maybe they were just impossible to put in place.
So before we even start thinking about what shade of welding lens to use, the employer has a legal duty. They have to perform a really thorough hazard assessment.
And it's to determine two things. One, is PPE even necessary? And two, if it is, what exactly is required? What type, what level of protection?
And the standard requires this because the hazards can come from anywhere. Processes, the environment, chemicals.
Radiological hazards, mechanical irritants. The list is wide, and the way you assess each one is, well, it's a completely different discipline.
Okay, let's talk about that. Let's break it down. If you're assessing a hazard from a process, say grinding metal, what does that assessment look like?
Okay, so for grinding, you're focused on mechanical irritants and impact energy. You're analyzing the speed of the grinder, the type of metal, the potential trajectory and speed of any flying bits.
So the PPE you choose is going to be directly based on that data.
Exactly. You'll end up selecting impact-rated safety glasses,
Yeah.
With the Z87.1 certification, probably a face shield too. And the conclusion of your assessment is that you just can't fully contain that debris with, say, machine guarding alone. So you have to rely on personal protection.
Okay, that makes sense. Now let's switch gears. What about an environmental hazard, like someone working outside in extreme cold? Or maybe in a super noisy factory.
That completely shifts the focus. Now you're looking at ambient exposure levels. For noise, the assessment means you're out there with a meter measuring decibels, and then you're calculating the specific noise reduction rating. the NRR, that the hearing protection needs to have.
And for the cold.
For cold, you're assessing temperature, wind chill, how long the person's going to be exposed. And that leads you to specialized clothing. Not just any winter coat, but something that is rated to maintain core body temperature against those specific quantified environmental conditions.
And then I imagine it gets way more complicated with chemical hazards.
Exponentially more complicated, yeah. Because now you're not just worried about a piece of metal hitting you, you're worried about absorption through the skin, inhalation, permeation.
So how do you even assess that?
It becomes highly scientific. You are completely reliant on the safety data sheet, the SDS, for that specific chemical. You have to know its concentration, its state. Is it a gas, a liquid? You need the permissible exposure limits, the PELs.
And how it gets into the body, the route of entry.
Exactly. Is it a skin hazard or an inhalation hazard?
Yeah.
A single chemical assessment could lead you to specifying a very particular type of chemical-resistant glove, one with a documented breakthrough time and a negative pressure respirator with very specific organic vapor cartridges.
That is a huge difference. You know, a standard leatherwork glove that's great for preventing scrapes is suddenly useless.
Or worse than useless.
Yeah.
It could be dangerous if it soaks up a hazardous solvent and holds it against the skin. The assessment has to pick the gear that resists that specific chemical.
And what about the last category, radiological hazards?
Yeah, that's less common in general industry, but where it exists, it's obviously critical.
So there, the assessment is all about monitoring and containment, right? Managing the dose.
It is. PPE in that world might be lead aprons, specialized shielding, disposable suits to stop you from, ingesting radioactive dust. It might even be the dosimeter itself, the little badge that tracks your exposure.
So the assessment isn't just about preventing an immediate injury. It's about preventing exposure from going over a legal limit over time.
And in every single one of these cases, the employer has to write it down. They have to document the assessment. It's a legal requirement to show how you decided PPE was needed, what you identified, and why the gear you chose is the right stuff.
Okay, so the assessment tells you what you need. But the employer's job doesn't stop there, right? It's not just about handing out the gear. There's that follow-up duty.
The duty to maintain. And honestly, this is where a lot of safety programs fall apart. The regulation says the employer has to make sure the equipment is kept in a sanitary and reliable condition.
Let's talk about reliable condition. That seems critical. For something that's your last line of defense, reliability is, well, it's everything.
Think about a hard hat. Its reliability is its structural integrity. It's designed to take a specific amount of impact. If it's been dropped from a high place or it's taken a hit, or maybe the suspension inside is cracked, its reliability is gone.
Even if the outside shell looks fine.
Even if it looks perfect. So the safety pro has to enforce really strict inspection rules daily or before every use and make sure compromised gear gets replaced immediately.
And maintenance also covers sanitation, something we've all become very aware of recently. Shared gear, especially something like a respirator, needs really careful cleaning protocols.
Meticulous protocols. And they have to be documented in your respiratory protection program. Otherwise, you're just trading a physical hazard for a biological one. If you issue a respirator, you have to ensure there's training on fit testing, on how to store it so it doesn't get crushed, and on exactly how to clean it.
So the duty to maintain is not just a suggestion.
Not at all. It's an ongoing resource-intensive part of the operation. And without it, the whole PPE program is just a false sense of security. And that, you could argue, is the most dangerous thing you can have on a job site.
That sets the stage perfectly. So we know selection is based on a technical, documented assessment. Now let's get into the specs themselves, starting with maybe the most rigorous area of all, protection against radiant energy. Okay, let's drill down into the incredible detail needed for protecting eyes and face during things like welding and cutting. This is not a place for guesswork. You have to know the physics.
Yeah, this is where safety management becomes really just applied physics. We're quantifying the exact barrier needed to protect the human retina from intense visible light, ultraviolet, UV, and infrared, IR, radiation.
We're pulling these details right from the source material, from Table 14.3, which lists the filter lenses for this purpose. And the key thing to see here is that the filter shade you need is determined by two things: the specific operation and the electric current measured in amps.
And we have to stop and emphasize just how fast a catastrophic permanent injury can happen here. A flash burn, what welders call welder's eye, is incredibly painful from just a brief exposure. But getting it wrong over and over again can cause permanent vision loss.
So those shade numbers, they're literally the difference between sight and blindness.
They are.
All right, let's start with shielded metal arc welding, SEM-OAW. Stick welding. For anyone listening who isn't a welder, what's the hazard profile here?
So stick welding is super common. You use a consumable electrode that's coated in flux. When you strike the arc, that flux burns off and creates a gas shield to protect the weld. The main hazards are that incredibly intense arc, but also a lot of spatter molten metal flying around and a lot of smoke and fumes.
And the intensity of that arc is directly tied to the electrode size and the amperage.
Directly. And the standard reflects that power curve perfectly.
So you have to be able to connect these amperage ranges to the right shades.
Right. So if you look at the low end, small electrodes, maybe less than 60 amps, the minimum shade required is a 7. That's your baseline. But listen to how fast it ramps up.
Okay.
When you move into heavier work, electrodes running between 160 and 250 amps, the minimum shade jumps to 10. And for the really heavy-duty stuff, 250 to 500 amps, you are required to have a minimum shade of 11.
That jump from 7 to 11.
Wow. It's not linear. And that's the key. A change of one shade number from 10 to 11, let's say, it represents an exponential reduction in the light getting through. It means a 500 amp arc is so much more intense that a shade 10 lens, which was fine at 250 amps, would be dangerously inadequate.
So the safety pro has to understand the logarithmic nature of the scale.
Yes, that is the critical distinction. It's not a simple sliding scale where a shade 9 is just a little less protection than a shade 10. The increase in optical density is huge.
Okay, so let's compare that to gas metal arc welding, GMAW, or MIG welding, and flex cord arc welding, FCAW.
Right, so with MIG, you're using a continuous wire and a shielding gas. It's often a cleaner weld, less spatter than stick welding, but you still have that intense radiation.
What's interesting in the table for GMAW and FCAW is how consistent the requirement is after a certain point. Under 60 amps, it's a shade 7, just like SNW. But from 60 amps all the way to 500 amps, it's a flat minimum of shade 10.
And that tells you something about the physics of that arc. It suggests that once a MIG arc is established at a moderate current, it puts out a consistently high level of radiation. So it needs that shade 10 floor, even as the current goes up.
So for a safety manager, that simplifies things a little bit. Once you're past the low setting, shade 10 is your go-to for those processes.
Up to 500 amps, yes. It creates a clear standard.
And then you have gas tungsten arc welding, GTAL, TIG welding. This is the precision stuff.
Very precise. It uses a non-consumable tungsten electrode and a separate filler rod, all shielded by a gas like argon. It's a very clean, low-spatter process.
And because the arc is cleaner, the shade requirements are a bit different.
They are. For TIG, once you're over 50 amps, you start at a minimum shade 8. And that holds all the way up to 150 amps. You only have to jump to a shade 10 when you get into that 150 to 500 amp range.
So let's compare. If you're stick welding at 100 amps, you need at least a shade 9. But if you're TIG welding at 100 amps, you only need a shade 8.
Exactly. And that tiny difference in the rule is based entirely on the physics of the arc and the type of shielding gas being used. For you, the safety professional, it means you can't just substitute things. The PPE has to be specified for the exact machine and method being used that day.
Okay, let's shift to cutting. Air carbon arc cutting. The table divides it into light, which is under 500 amps, and heavy, which is 500 to 1,000 amps. But here's the odd thing. They both require a minimum shade of 10.
Yeah, that's a really strong clue about how intense a carbon arc is. Even the light end of the process, which is still a massive 500 amps, demands that high level of protection.
But the real granularity comes with plasma arc operations. This where it gets super specific.
It really does. Let's look at plasma arc welding, or PAW. The ranges are so tight.
Okay, read them out.
Under 20 amps, you need a shade 6. From 20 to 100 amps, it's shade 8. From 100 to 400 amps, shade 10. And from 400 to 800 amps, shade 11.
That's 4 distinct categories. So if your machine is set to 19 amps, shade 6 is fine. But if you nudge it up to 21 amps, you are instantly out of compliance if you haven't switched to a shade 8 lens.
And those machines allow for instant changes in current. So your safety system has to be just as fluid. Maybe that means using auto-darkening helmets. But even then, the safety manager has to make sure the helmet's maximum shade capability can handle the machine's maximum output.
Plasma arc cutting is just as specific. Light cutting under 300 amps is shade 8. Medium, 300 to 400 amps, is shade 9. And heavy, 400 to 800 amps, is shade 10.
Here it is again, the importance of the specific process. A shade 9 lens is perfectly fine for medium plasma cutting, but it's totally insufficient for heavy cutting. That one shade difference is everything.
And just to put all this in perspective, think about the really low energy stuff. Torch brazing only needs a shade 3. Torch soldering, a shade 2.
Completely different hazard profiles. But then you hit the big one, the outlier in the source material, carbon arc welding. It requires a minimum protective shade of 14.
14. A shade 14. Why is that so much higher than anything else? Even high amp-stick welding is only an 11.
It's a fascinating question, and it goes back to the physics of that specific process. Carbon arc welding is an older method. It uses 2 carbon electrodes, and it creates this enormous cloud of incandescent carbon vapor. The arc is just phenomenally, blindingly bright.
So it's putting out way more radiant energy.
Far more. So the safety pro has to know, even if they only see this process once in a blue moon, that it requires a very special maximum rated filter. Nothing else will do.
So the takeaway for you, the person listening, is that this standard isn't arbitrary. It's a protection equation.
It's exactly that. The difference between a shade 9 and a shade 10 is the difference between being compliant and being in violation. But more importantly, it's the difference between adequate protection and a life-altering injury. You have to treat these charts as engineering specs, not guidelines.
Okay. Let's move from protecting against photons to protecting against physical force, impact, punctures, and electricity. Let's talk about extremities.
Right, so we're moving from high-frequency energy to kinetic energy, compression, and electrical current. Hands and feet.
It's a whole different world, protecting the body from what you can't see versus what you can, like a falling object.
Exactly.
So, safety footwear, the requirements sound simple on the surface, sturdy, with an impact-resistant toe. But, you know, the devil is always in the details.
It is. Impact resistant isn't just a vague term. It means the toe box has to be able to withstand a very specific amount of force before it deforms enough to cause an injury. This is all governed by ANSI STEM standards for compression and impact.
So when you're buying safety shoes, you have to be looking for that specific compliance rating.
You have to. You need to ensure it meets those minimum force thresholds for your workplace hazards.
And the sturdiness requirement goes beyond just the toe, right? The source material mentions puncture protection.
Yes, and that's a perfect example of the hazard assessment driving the PPE selection. If you're in a warehouse, impact protection from moving carts is probably your main concern. But if you're on a construction site,
nails, screws, rebar.
Exactly. Puncture protection from sharp debris becomes the top priority, and the safety manager has to confirm that the shoe, whether it has a metal or a composite insole, meets that documented puncture resistance standard.
Okay, let's move up to hand protection. This is another area where the technical details are absolutely non-negotiable, especially with electrical safety.
Oh, absolutely. I mean, hand protection is so diverse. You've got everything from simple leather gloves for abrasion all the way to, multi-layered gloves that resist chemical permeation, but nothing is more critical or more quantified than the rubber insulating equipment used to protect against shock.
So here you're relying entirely on the specific ANSI STM standards. You can't just go out and buy a thick rubber glove from the hardware store.
No, it has to be tested, certified, and rated for the specific voltage you're going to encounter. The integrity of that gear depends on following those standards to the letter. And the standards are numerical requirements. They are tested and they are dated.
Let's look at some of the ones in Table 14.4. For rubber insulating gloves, it lists ASTM D12087.
And for rubber matting, which you'd use around electrical panels, it's ASTM D17888 or the 93 version.
Okay, let's pause on that designation. ASTM, that's the American Society for Testing and Materials.
Right. They're the ones who develop and publish these technical standards.
Yeah.
So D120 is the specific standard for rubber insulating gloves. But the number that comes after it, the NIC87, that's the year.
The year it was adopted or last revised, and that specific detail, D12087, is incredibly important.
It's critical. It speaks directly to your compliance. Standards are always evolving. They get updated, they get revised. By calling out a specific dated standard, OSHA is saying your gear must conform to the testing methods and specifications of that year.
So what happens if a manufacturer comes out with a new glove that meets, say, D12009, the 2009 standard, which is probably better, but the regulation you're working under still only lists D12087?
That's a compliance trap, a really dangerous one. While the new glove is probably superior, a compliance officer who is going by the letter of the law could cite you for being non-compliant.
Wow. So it forces the safety professional to be a compliance historian.
You have to be. You have to rigorously verify which standards are acceptable. And this isn't just for gloves. It applies to all the related gear in the source material.
Right, like rubber insulating blankets. They had to meet ASTM D 104893 or Quinhel 4880A. And you even have that little A sub-designation.
That's the level of detail we're talking about. It indicates a specific minor change within that year's standard. Same thing for insulating sleeves, hoods. It's all governed by these specific dated standards.
So what does this mean in the real world for a safety manager?
It means you have to build your entire inventory and maintenance system around these dates. You need to make sure that the required dielectric testing and recertification of your gloves is being done according to the methods laid out in that specific dated standard.
If you use the wrong testing method, the certification is invalid.
And the gloves become unreliable and non-compliant. It's a perfect example of an administrative control that has to support an engineering control. You can have the best glove in the world, but if your paperwork, your procurement process, your retesting schedule isn't right, the whole system just falls apart.
It's a very high bar for professional competence.
It is. When you're dealing with a hazard like electricity where failure is instant death, there's just no room for good enough. Everything has to be quantified, traceable, and tested to the exact spec.
Okay, let's take a step back now and connect all of this. The Shade 10 lens, the D120-87 glove. Let's connect it to the bigger picture of workplace safety.
Yeah, that's a good idea.
The source material brings up other safety systems, and you really can't understand Chapter 14 in a vacuum. The most direct connection is to the control of hazardous energy. Lockout to gout, LO2.
Right, LO2. That's the standard for preventing machines from starting up unexpectedly during maintenance. It's an administrative and engineering control. You de-energize the machine and physically lock the power source.
So, if you've done a LOTO correctly, the machine has no power. So why do we still require people to wear these highly specific ASTM-certified insulating gloves and mats?
Because ULTO is procedure. And procedures can fail. PPE is the safety net for when that administrative process breaks down.
Human error, for example. On a complex machine, you might miss one of the energy sources when you're applying the locks.
Exactly. So those D120-87 gloves are your protection against that unexpected re-energization.
Yeah.
They're your insurance against stored energy that wasn't bled off correctly. A capacitor, a pressurized hydraulic line.
And what about proximity hazards?
That's the other big one. You might be working on a machine that's perfectly locked out, but right next to you is another piece of equipment that's still live because it runs a critical system for the plant.
So the mats and gloves are isolating you from those adjacent energy sources.
Precisely. They are outside the scope of your ULTO, but still within reach. The high-tech specs of the PPE are needed because the hazard, even though it's been controlled, hasn't been completely eliminated from the workspace. It is the backup for the backup.
So compliance with the LOTO standard and compliance with the PPE standard they're inseparable.
They have to be. And you can draw a similar line to construction safety. We've talked a lot about welding and electrical work, but construction is full of quantified PPE.
Fall protection is the obvious one.
Absolutely. A fall arrest harness is not just a bunch of straps. It's an engineered system. It's designed to stop a fall within a specific distance and limit the arrest force on the person's body.
And the safety pro has to know all the numbers. The free fall distance, the lanyard length, the deceleration distance.
You have to do the math. If you're working 18 feet up and your lanyard is 6 feet long and your shock absorber needs 3.5 feet to deploy, you have a very precise limit on how far your anchor point can be from the edge.
And it extends to things like safety nets, too. The rules there are also about specific numbers.
Right. The Force mentions things like the working surface can't be more than 5 feet vertically above the net, and the net has to extend at least 8 feet horizontally from the edge of the work surface.
So again, precise numbers. 5 feet vertical, 8 feet horizontal. It's the same theme everywhere. Whether it's a Shade 14 filter, a NACNIS 87 ASTM standard for a glove, or a 5-foot max drop for a net, it's all about quantifiable, non-negotiable specification.
But the big idea, the philosophical framework that holds all of this together, is the hierarchy of controls.
Okay, let's run through it. Avoidance, elimination, substitution, engineering controls, warnings, administrative controls. And then at the very bottom,
Personal protective equipment, last on the list.
And that's the key insight. That's why Chapter 14 even exists. The incredible granular detail in these PPE standards is really just a formal admission that we failed to make the workplace safe through better methods.
Exactly. If we could just eliminate the welding process, we wouldn't need a Shade 10 lens. If we could substitute a dangerous chemical for a safe one, we wouldn't need those special gloves. If we could engineer a ventilation system that captured 100% of the fumes.
We wouldn't need respirators.
But we can't always do those things. We have to do that 500 amp weld, so the danger is still there. The standard then says that residual risk has to be managed by putting a quantified barrier directly on the person. The toughness of the rules in Chapter 14 is directly proportional to the danger of the task that we couldn't engineer away.
So when you're looking at that table of filter shades, you're not just looking at a checklist. You're looking at the result of decades of research into what a 450 amp arc does to the human eye.
And the conclusion of that research is that the only acceptable defense is a barrier that is certified to that exact level of optical density, which we call the shade 11. It's a continuous reminder to the safety professional to always be trying to push safety controls up the hierarchy.
That's a great point. If you find yourself managing a huge, complicated PPE program, it might be a signal that you need to reevaluate your engineering controls.
It should be a trigger for that conversation, yes.
This has been a really comprehensive deep dive. We've gone way beyond just a surface-level look at PPC. We've established it's an exact science, starting with a hazard assessment and demanding precise, quantified adherence to standards.
And the goal is always the same. Protect the individual when all the other controls have failed. And that protection only works if the safety professional has mastered these technical details, because a single shade number off or the wrong revision year on a standard, it can lead to catastrophe.
Knowing these quantifiable rules is what separates just handing out gear from actually managing risk.
It's the definition of professional competence in a high-hazard job. And hopefully this long explanation has given you the detail you were looking for.
I think so. So to wrap up, let's leave you with our final provocative thought. Let's connect all this technical specificity to the reality of making it work on the ground.
We've talked a lot about the challenge of buying the right stuff. Did we get the right shade, the right standard of glove?
But the real challenge for the safety pro on the floor is application and verification. Let's say you have a welder who, in one shift, is doing 3 different jobs. SMA at 100 amps, that's shade 9. Then GTTA at 100 amps, that's shade 8. And then GMAW at 200 amps, that's shade 10.
So they're supposed to be swapping between 3 different shades.
Right. How do you design a system that prevents them from grabbing the wrong lens by mistake? If their protection depends entirely on them remembering that a fractional change in current or process requires a different piece of gear, what's your responsibility in designing a system that makes that foolproof?
Visual aids, maybe machine interlocks, a simplified inventory system.
Yeah.
Something that takes the burden off of human memory.
How do you verify application in real time? Do you just do random audits, or do you make a rule that says everyone has to use the highest possible shade for all jobs, even if it makes it harder to see the lighter work?
And that's the management challenge, isn't it? It's moving past paper compliance to ensuring that this highly specific standard is being applied correctly, consistently, in the moment of highest risk. It forces you to think about how you verify compliance when the weak point is the human brain dealing with technical details.
How do you measure it? How do you train for it? How do you audit for it on your site right now?
That's your challenge for this week. Thank you for joining us for the deep dive.
We'll see you next time. Until then, stay safe and stay informed.